This is a discussion of the definition of a limit of a function. And the standard definition is if you have a domain A and C is the limit point of A, the limit as x approaches C of f of x equals L. It's barely legible. If and only for all epsilon there exists a delta such that whenever x is within delta of C and x is in A, it follows that f of x is within epsilon of L. And topologically, we can just rephrase that, and that says, right, same domain, same limit point C, same limit, if and only for all epsilon neighborhoods of L, which means basically f of x is in the epsilon neighborhood of L is what this says. There exists a delta neighborhood of C, which means basically this, such that that whenever x is in a delta neighborhood, basically whenever this is true, f of x is in an epsilon neighborhood, which means that's true. So these are really saying the same thing. And now I'm going to look at a graphical example, and I'm going to explain to you kind of what this is saying. So the first thing I'm going to do is write for all epsilon bigger than 0. So what we're going to do is we're going to fix an epsilon bigger than 0. And so what I'm going to do, maybe this is epsilon. Here's L plus epsilon. Here's L minus epsilon. And so anything in between here satisfies whatever minus L is less than epsilon. Also, anything in between here satisfies, if you have a point y here, satisfies y is in the epsilon neighborhood of L. These two really mean the same thing, but the way I want to think about this is I'm just going to create a tube, a red tube that kind of goes all the way around. And basically it says the function has to be within this tube as long as we're close enough. Now look, sometimes, oh by the way, this function f in black, notice how it's nasty, it's kind of cut up and goes all over which way. That's because functions aren't necessarily continuous. Now we'll work with a more general function. So I need to find so given this, right, I need to make sure that as long as I'm close to C, I'm between these two red lines. So sometimes I'm outside, sometimes I'm not outside of the red lines, but as long as I'm close to C, I need to be within the red lines. Specifically, I need to say how close I need to be to C, which is going to be my delta, to guarantee that I'm within those lines. So here's our hero of the day, delta. And notice that as long as between here and here, I'm within those red lines, so I can go something like that. So assuming that these are equal lengths, just take whichever one's greater, this is what I'm going to let my delta be. My delta is just going to be that much. So this would be C minus delta, C plus delta, and this would be my delta neighborhood. So my delta neighborhood of C is just going to equal C minus delta, C plus delta, and very similarly, my epsilon neighborhood of L is going to equal L minus epsilon, L plus epsilon. So what have we done? For all epsilon bigger than 0, okay, give me your favorite epsilon. Whatever epsilon it is, I can make this little tube. There exists a delta bigger than 0. So basically, as long as you're within here, as long as you're a valid input, it follows that as long as you pick any x in here, so I could pick that x, I could pick that x, I couldn't pick that x because that's way outside, so that's no good. Boom, nope. If I pick any x in here and I go up and see what it graphs to, there's my f of x. And notice two things. F of x is between L minus epsilon and L plus epsilon. F of x is between these two. So a short way of saying that is this. Another way of saying that is that f of x is between these two things, which means it's within epsilon of L, which means it's within this epsilon neighborhood, which means exactly this. And also, just to get another color in here, notice my x. My x means two things. It's between C minus delta and C plus delta, which means it's exactly in there, or it's within the delta neighborhood. So it's within that. That's the definition. I hope that helps.